Hello everyone, welcome to the PETR2131. This is the last lecture of the topic 3, the loss of containment, and at this lecture we'll learn on the Faultry analysis. As you already know, like at the previous lecture we have learned on the event analysis, and also we went through several definitions. The definitions that we'll actually use in here at the Faultry analysis, and also we actually use those in events, like what are the basic event, top events, etc. Okay, so the Faultry analysis represents the graphical relationship among the events and the unwanted events using the logic gates. It starts with the top events and reveal the basic cause of the top events in a deductive way. And the relationship between the events are expressed in and, okay, that means the intersection, and or logic gates, that means the unions. Okay, probably you know that. It quantifies the probability of occurrence of an incident using the fault tree and the basic failure data. Okay, so that's how we actually can quantify the probability of occurrence. Okay, and if we get the probability of occurrence or probability of frequency, then we multiply with the consequence, then we'll get the probability of failure. Okay, so this is this small f is the for frequency, and this big F is the for failure actually. So it identified the system's weakest link through the cut sets. We'll see that it evaluates in common mode failure. Okay, so you'll find lots of similarities of using the Faultry analysis on the flowchart. Okay, so the top event, this is the top event, and that's how the it looks like. The top events and the intermediate events actually denotes as the rectangular shape, but the basic events are these round, the circular shape. Okay, so what is the basic event? Basic events, the fault event needs no further definition. That means it's the base of the basic events. All right, we'll actually see how the basic events actually work. So this is OR gate. OR gate means like it would be like the output of the gate that will occur if any of the input occurs. For instance, one incident could happen due to this 1 2 3 reasons. So if any of these 3 reasons actually happen, then the incident could occur. So that means this is an OR gate. Okay, like any of these 3, or in here it's 4, any of these 4 events actually occur, this incident could actually occur. So that is the definition of OR gate. But this denotes the AND gate. And what is AND gate? AND gate means either this and this, these 2 events must satisfy, okay, must occur to satisfy the AND gate, okay, to activate it. That means to this event, these 2 cases must satisfy. Okay, and this is the transfer gate. That means if you don't have the enough space in one page, you can actually use this symbol and work at the different page, I mean the next page. Okay, so this is about the fault-free analysis, the symbols. Now, how this fault tree actually looks like and how it actually works. For instance, let me give you an example that will be the best idea. For instance, you don't have any light, like you turn on the switch and the light didn't work. Okay, why the light bulb does not illuminate? So like there are lots of issues could associated for the illumination of the light bulb. For instance, the filament of the light bulb, it fails to open. That means like the filament could go wrong, okay, or the socket terminals that could have the contamination, or there is no electrical energy at the socket, or the light bulb is not fully screwed in. So here, if the filament fails to open, there is no further way to down. We already have identified the cause, okay, the root cause, okay. So this is the root cause. That means the base event actually based on the root cause. Probably you heard about like the root cause analysis, or RCA. So we actually do the root cause analysis in a very similar fashion, okay, to find the root cause in such a way. So this is a kind of like, we call like the base event or the root cause, okay. So if the filament fails to open, then we know what's happened. Then we should actually go to the store and change the bulb, okay. Or if there is a contaminated socket terminal, then what we can do, we can, like as you see, is the undeveloped event that we cannot go further due to the lack of information. If this is contaminated, then if you don't know what to do, you got to call an electrician, and that's they can actually check and find what you can do. Or like the light bulb not fully screwed in. So like if not, it's fully screwed in, so you know what to do. You can actually like the screwed in properly and turn on the light, or you can clear the contamination by yourself or the electrician, and you can actually turn on the light, okay. Now what's happened if there is no electrical energy in the socket? Then you got to investigate further what you got to do, and then there are several other reasons for that. Maybe there is a short circuit. If there's a short circuit, there's nothing we can do more. So this became a base event, okay. There's a wiring, the open circuit. That's also with the base event. There is no electrical energy in the socket, okay. We'll see that later. And the socket is disconnected from the wiring, so you can just connect it and work on that, and that's how you can actually turn on the light. Now if there is no electrical energy on the socket, then what could be the probable reason? Probably the switch fails to open, probably no electrical energy on the wiring and the switch, or the operator does not attach the switch. If this switch fails to open, then you got to change the switch, and that's it. If operator does not actuate the switch, you just need to turn on the switch, okay. Like you just on, it will work. Now if no electrical energy on the wiring to switch, there could be several other possibilities. For instance, the wiring could have short circuit, the wiring could be an open circuit, and no power from the source, okay. That means there could be load shedding. So if there is a load shedding, then when the electricity will be coming in, after that you can work on that. So these events are the base events, all right. Now if we actually want to calculate the probability, then how we can actually calculate? So we'll actually see just exact thing, like how we can actually calculate the probability of all these events, okay, all these events, and then we'll find the probability of the failure of the final event, okay. That's how the fault tree actually works. Now to calculate the probability of the failure, we use the rules of Boolean algebra. And how this Boolean algebra works, if you have idea about computer programming, then probably you know how the Boolean algebra works. It's based on the set theory, but I'm showing you again. So is the cumulative rule. P1 times P2 equal to P2 times P1, or P1 plus P2 is equal to P2 plus P1. It's the same, so you can actually put this or this. It's the same. Okay. Now associative rules, that means P1 times P2 times P3, the same meaning of P1 times P2, the bracket, times the P3 outside, and the same way the unions actually do. So these are the intersections. Okay, so for instance, P1 intersection of P2, that means P1 times P2. But if the P1 union P2, that means P1 plus P2. Okay, so the distributive rule is P1 times P2 plus P3 equal to P1 times P2 plus P1 times P3, the same way. Okay, this is the the distributive rule is this one. This is the idempotent rule. Okay, and this is the rule of absorption. Okay, so so this is all the rules actually we need to calculate the Boolean algebra. Okay, so let's do a math, and then we can actually get to know about the better. So the question is there is a propane offloading area near the Sydney Harbour. Okay, Sydney Harbour, Cape Breton, is showing in the picture here. At the Sydney Harbour area is a propane tank. Okay, so the ship comes in and put the propane in the tank. So you are transferring the propane to the tanker. All right, now a fire accident may occur due to release of this propane. As a safety measure, a gas detector alarm is installed in here. Okay, just like the fire alarm. Okay, so if there is how the fire alarm actually works. So fire alarm actually works like if there is a heat or smoke, then it got the detector, and from the detector set off, and the fire alarm actually turns on. And same way, if there is a release of the propane, then this detector actually at the signal, and that it will turn on the gas detector system. Okay, it is important to note that the gas detector is ineffective for catastrophic failure, for instance the tank rupture. So if there's a tank rupture, then the whole system will blow up. Okay, so the gas detector won't work in that failure. For other system failure, the gas detector will work. Okay, now calculate the probability of fire incident PF using the Faultry analysis. Now how can we do that? The informations are given that the leak during downloading of propane from tanker. So downloading the propane from the tanker, the risk is given 0.08, and it is frequency per month. Okay, leak from the valve, there's a valve attached, there could be some leak from the valve too, and the frequency is given 0.03. Leak from the pipeline, so there's the pipeline too, so it's a piping works right here and here, so the pipeline could also leak, and the value is 0.05. Failure of the tank due to catastrophe like a rupture, maybe the tank could actually blast. Okay, so that probability is given 0.005, which is very low, right? The presence of ignition source, well, if there is a presence of ignition source, then there is a high chance the incident could actually happen, and that is 0.05. And there could be another problem, that the gas detector alarm fails, and that would be 0.02, the rate of occurrence. Okay, so all these frequencies, that means the frequencies are actually given. Okay, so we have to calculate the probability of the fire incident in the fault tree analysis. So the first thing we need to do, we need to develop the fault tree, and then we'll do the calculation. So let's see how we can actually develop the fault tree. So the first thing is the fire incident. Okay, now the fire incident could be happen in, if you know about the fire triangle. So the fire triangle means any kind of like fire incident need three things. Number one, source. Okay, number two, ignition source or like spark, and number three, oxygen. Since it's actually in the open area, so there is a abundance of oxygen if there is any ignition, and if there is any leakage source, then there is a chance of fire incident. Okay, so the fire incident, I mean, since the oxygen is in everywhere, so we can actually care about like the ignition source and the leakage source. Okay, so ignition source, this would be the base event, any types of ignition source, because we already have information on the ignition source. What is that? Presence of ignition source is 0.005. Now this would be AND. Why? Because just only the ignition source you have, you don't have any release, fire incident won't occur, or you have the leakage but there is no ignition, also the fire incident won't occur. So that's exactly why this is AND gate. Okay, now release of the propane, how the propane could release from this system. Okay, yeah, the system actually picture is over here already. So how there could be a release? So there could be a catastrophic failure of the tank, or there could be a system failure from the pipings, right? So the catastrophic failure value is also given, the failure of the tank, which is 0.005, right? And there is also a system failure. So this would be this or this. Okay, now the system failure would occur, again there are two differences. One, if there is any leakage, and if the gas detector don't work. Well, just imagine if there is any leakage but the gas detector works, then you can actually shut off the system, right? So that means these two actually have to both in the same order, the simultaneously. Okay, so the gas detector should fail and there would be a leakage. So that's why there is a AND gate in here, and there is a OR gate in this case. All right, clear? Now if the gas detector fails, then we have the probability also of the gas detector fails in here. All right, now leakage, there could be a couple of potential for the leakage. For instance, leakage from the pipeline, leakage from the valve, or leakage from this tanker. Okay, so these are again the base events. So how many base events we got? Failure of the tank, leakage from the pipeline, leakage from the valves, leakage from the tanker, and gas detector fails, and ignition source. That means 1, 2, 3, 4, 5, 6, total 6 base events we got. Okay, so the 6 total root causes total cause we need for the fire incident. Now let's calculate it. We have all the information. So we have leakage from 1, from the valve, from the pipeline, failure of the tank due to catastrophe, presence of ignition source, and the gas detector alarm fails. That means we already have 6 base events already. Now it's time to calculate. We have all the informations, right? And we get the diagrams too. So how we can actually calculate? So we have the rate of occurrence, which is lambda, okay, 0.08. Now we know from the previous slide, remember, that we can calculate the reliability, which is e to the power minus lambda t. So that means if it's lambda, r equal to e to the power minus 0.08 times t. T is equal to 1 month, okay, because the frequency is given in month. So we'll get the value of reliability. And what is the value we got? We got 0.0923. Now the probability is, if the probability is 1 minus reliability, okay, so that means we get the probability, this value. So let's denote this, the probability of PD, okay, the leakage during the probability of the tanker, PD. Just like that, we can actually calculate the probability of the failure for all these events, right? For all these events, we can actually calculate the probability. I will not show the results. You can actually do it by yourself, okay? And the notation would be the PLV, LP, CT, CFT, okay? Like the PI for the ignition source, PA for the alarm. That means alarm fails, PA the probability, okay? Ignition source, PI, catastrophic failure, CFT, leak from pipeline, LP, leak from valve, LV, okay, and the leak during the downloading from the propane, PD, okay. So this is how we actually denote it. Now, how we can actually calculate? So first, we have these three informations, PLP, we got from here, okay, LV, same LT, okay, and then we have this OR gate. So probability of leakage due to pipeline, valve, and the tanker are this, okay. So how we can actually calculate this? Probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B, probability of B intersection C, probability of C intersection A plus probability of A intersection B intersection C, okay. And what is the formula for probability of A intersection B intersection C? Is probability of A times probability of B times probability of C, that we can actually put in here. And what is the formula for the probability of A intersection B? Is probability of A times probability of B. The same way, probability of B times C, probability of C times A. And we also know probability of A union B is probability of A plus probability of B minus probability of A times B. Alright, so we got all the formulas. Now, so we can calculate PL using this, and then we'll have the PL intersection of PA, okay. So we'll get the system failure, PS, from this information. Then again, we already have probability of CFT and we have probability of S. That means we can actually calculate the release of propane, PR equal to P of CFT union of P of S, okay. Then we can actually calculate the PFR. Now we also have the probability of ignition, and then we have calculated the probability of release of propane. Then it's an AND gate. So again, P union E, that means P of R times P of I, right? Here, what is that? P of CFT plus P of S minus P of CFT times P of S, right? The same thing. Here is the P of L times P of A, right? And here you know how to do this formula. So from calculating all these values, you will get the probability of fire incident. That's what we actually need. All right. Now, if you got the probability, then how you can actually calculate the risk? If you have the probability, if you have the PF, then you have to multiply with the consequence of the incident. Now, at this section, the consequence will not go through that, how to calculate the consequence, because it's another very vast and bigger sections. So just imagine, like, I mean, if there is a fire incident, there could be a very severe consequence, and in most cases, we actually put a consequence in a. It's easier to put in a monetary value. For instance, in case of any kind of fire incident, we have a consequence for if that happened in Sydney Harbour, we got like 7 million. Okay, and if the probability is, for instance, 10 to the power minus 3, so 10 to the power minus 3 times 7 million will get a value. Okay, so that value would be a risk in that case. Okay, so the risk of the whole system. Now, this risk, you remember, like, I mean, we said the risk in the reference, that health and safety, it means like the combination of probability of hazard causing incident and the consequence of the incident, right? So this is how we calculate the risk. Now, this risk is very important. Why this is important? It's very important because for any types of operations, we need a number of the risk, and that's how give you an example. I mean, very interesting example would be, that's how your every insurance premium actually works, using same formula, exactly same formula, goes in the same methods of analysis and everything. How we have developed an algorithm. They have this algorithm right now. Okay, so what is this algorithm? This algorithm got that if it's a snowy day, if it's the location in this, that means like the frequency of the incident is, for instance, you live in Toronto, okay, and you live in near the Markham, or like, I mean, Brampton in Toronto. So there's a high chance that you have, I mean, the frequency, or like the probability of the incident in while driving car in Brampton is way higher than anywhere in Canada. Okay, and the consequence would be also high, because they have like lots of like highways, and the cars would actually drive in overspeed. So there could be a potential, like, loss of valuable assets. Okay, so that's exactly why, since the probability is higher and also the consequence higher, that means the risk is higher, and that's exactly why your risk premium is very high. So that's one of the reasons why Brampton, or like, I mean, Richmond Hill, in the whole Toronto area, even within the Toronto area, those areas got like lots of high insurance premium. Okay, so that's how they actually work on that. So any type of insurance, and also like, I mean, all the engineering calculation, we use this formula actually to calculate. Okay, so I guess we have learned something new, right? We have learned something new, how to do this calculation, and how actually the risk actually works, why the risk profiling is very important, why the risk assessment is very important, and how we actually determine the risk. Okay, so we've learned a very, I think, like, it's a very valuable lesson for your future career. Anyways, so based on this risk value, as I said, like, there's a high there's a high red zone area. Okay, so there's some high risk. So based on this, actually, there's a matrix. We can actually develop a matrix, okay? And in this matrix is like this way. Here is the risk, increment of the risk, and here is the probability, okay? So this is the probability of occurrence, and here is the consequence. And this is like more catastrophic, here is low, and this is like high the frequency is actually is in this way. So this is like a highly frequent, and this is low and very unlikely. So if you draw this, that means in this quadrant, what's happened? The consequence catastrophic and high frequency. That means this is in extreme risk, because remember, risk is equal to probability of failure or probability of occurrence is the same times the consequence, or like the severity of the consequence, okay? Now just think about this one. What is this? The medium risk. Why? Because the probability is at the middle and the consequence is moderate, so that's why it's in medium risk, it's in yellow zone. But you think about this one here, we got like the less frequency, okay? This is the high frequency zone, this is the low frequency zone, or like the low occurrence zone, and the probability is like minor to moderate. That means although the probability is moderate, but since it's low frequency, that's why this is low risk. But here the severity is moderate, but it's very high frequency, that's why it's also high risk area, okay? This is the probability of failure is minor and the consequence is minor, so that means it's in low risk area. So this is how actually we can determine, like evaluate actually the risk, okay? All right, so let's give another example how to evaluate the risk, like the ship to ship transfer. Okay, so here's the ship and another ship is transferring the fuel. Now what are the hazards associated with that? What are the risks involved, and how we can actually reduce the risk? It's your turn to get the answers, okay? Now let's talk about, like, we already have talked about, like, how to evaluate the risk, and let's talk about, like, how we can actually what strategy we can take to mitigate the risk, okay? One of the most important part of, like, mitigating the risk is the due diligence. And due diligence means, like, you act carefully when you have to act, okay? And the due diligence in many cases analyze the hazard and risk, bringing the risk of an incident to an acceptable level. What does that mean? That means that we cannot eliminate the risk at all. It is risk in every act, okay? Like, for instance, I give an example, like driving a car is risky, but it doesn't mean that we want to drive a car. We will drive a car, but we'll have all the safety gears. That's how we can reduce the risk in an acceptable level. Now, how we can determine what is the acceptable level? So that's why we have developed a tool. For instance, for driving the car, the first thing, your car should have a regular maintenance, right? Number two is, like, if it's the winter season, you will have the winter tire. You got the seat belt, your headlights and everything actually works, okay? And you abide by all the rules and regulations, okay? So this is how we can actually make sure, all right, so that's enough to have the to be the acceptable level to drive a car. And who will actually take care of this? Who will actually see that you are not overspeeding? The very important one, okay? So who will actually monitor this? Police will actually monitor that, Okay, and in the case of engineering, the inspectors, or like the who actually do the safety inspector or safety assessments, or like the safety committee, they will actually monitor and set the acceptable level. Okay, so that's why it called ALARP, or as low as reasonably practicable. Okay, remember that. Now, what is ALARP? ALARP is a conjunction with safety critical system where potential hazard is inevitable. Okay, for example, petroleum industries, nuclear plants, everywhere we can have the potential human injury or life or economic loss is present, but we cannot remove the system, right? We cannot remove the risk from the system at all. But ALARP, it says to accept a reasonably low amount of risk, and which is greater than zero, of course. I mean, there is risk everywhere, but it should be very reasonable. Okay, few examples, as I give some example of driving the car, or like operator need additional trainings using PPE. For instance, right now we have the pandemic and we should wear the mask, so this is how, I mean, gloves and mask and maintaining the distance is one of the perfect example of like ALARP. Like, I mean, we know there's a risk to go outside, but we have to go outside sometimes for shopping, or like, I mean, for the groceries and stuff, but we will use the safety gears. So that's an example of ALARP. Okay, so the ALARP diagram shows like the tolerable limit in this way. So this is intolerable zone. This is the tolerable zone only if reduction implicable of its own cost grossly disproportionate to the improvement gain. Okay, that means the risk can be undertaken if we use the proper safety measures. Okay, and here the broadly acceptable reason. Okay, so this is how the ALARP actually work. Now, how can we actually reduce the risk? Like here, from this point of ALARP, how can we come to this point? Okay, how can we take this journey to down here? There are a couple of ways we can actually do that. This is actually called the hierarchy of controls. Okay, very important. So this is the most effective and this is least effective. This is the way of effectiveness. Okay, so the elimination, like if you eliminate the risk or physically remove the hazard, that's the best way to remove that, and best effective way to reduce the hazard. Okay, if you cannot eliminate it, put a better substitution to replace the hazard with a safe one. If you cannot do it at all, then take the engineering control, which is isolate people from the hazard. Okay, and that's the thing we actually do during this pandemic too. Remember, self-isolation, that is a kind of like engineering control we are doing. If you still cannot do that, you have to go with the administrative control. Okay, so these are less effective. Like, I mean, elimination, I mean, substitution is less effective than the elimination, or engineering control is less effective than the substitution, and admin control is less effective than the engineering control. And what is that? Change the way people work. So you let people work, but you change the way, because right now, I mean, if you cannot isolate, you have to use PPE. Okay, sorry, the PPE is coming later. You have to maintain the safe distance and everything. Okay, so these are the things. And still, if you cannot do that, at that time you should actually use the protection, like the PPE. Okay, so this is the least effective way to control the hazard. So, well, I hope you have learned sort of thing about the risk, hazard, how to evaluate hazard, and how can we actually, what are the strategies we can actually take to mitigate and control. So this is all about the loss of containment, and hope you have learned new things in this class. And if you have any question, just let me know. You have the live sessions for we have the live sessions for the question and answer, and also you can email me, or at the Moodle you can just go to the Q&A section and put your comments in there, and if you have any confusion, please let me know. Alright, so good luck everyone, and have a good day. See you next class. Bye.